Okay, this is the first semester performance test review. I'm going to go through with you fairly quickly here. I'm going to go ahead and pull up my calculator. We'll be using our graphing calculators as we go throughout this. I'll be doing certain things I'll demonstrate on one problem and then may reference it on the next. So a little review on the graphing calculator. Okay, so my calculator is up and ready to go. Let's go ahead and go through this. The first thing we're going to do is, it says the concentration, problem number 1, the concentration C of a medication in the bloodstream, T hours after being administered, is modeled by the function, and you're given a concentration function there. It's to the 4th power. So we're going to type that in to our calculator. So let's go ahead and do that. I'm in math type. If you're in classic mode, you'll see a little caret key. It looks like this right here, right in the clear button instead of the math type. So just a reminder of that. If you're in math type, you'll have to hit the right arrow to get back down so it doesn't just type the rest of this out in the power. I'm just going to check that I typed this in right. Lots of decimals in 0.89. I'm putting an X instead of T here. Alright, so it looks like we're good there. We've got it all typed in. Typically what I'll do is when I go to graph it, maybe hit zoom and Z standard to start with and see how it goes here. We'll kind of graph it and then we'll need to maybe adjust from there, see how it does. Looks like we've got everything we need within the window. You can see starting at the origin here, this is all we really care about, is from the origin over to this first or other 0 past the origin. So there's our model. That's probably a pretty good window. It says in part A, what is the concentration of medication 1 hour after being administered? So if I want to know the concentration 1 hour after being administered, what I'm being asked to do is plug in 1 for T. So the calculator has a function called value. After you've graphed it, you hit second calculate value and just plug in 1. T is in hours. Hit enter and it gives me the value of 0.786. So our first solution here is 0.786. That's the concentration of medication 1 hour after being administered. Then it says, after how many hours will the concentration be highest? That word highest is asking for a max. So after how many hours, I'm just asking for the T, or on your graphic calculator, the X coordinate at which it reaches its high point. If we go back and look at the graph here, you can see as I trace along here, I'll do a trace here, kind of estimate about, I'm just tracing my little Frogger guy along here, but somewhere around here I reach a maximum point. You can see where this is over here. And we want to find the value of that. Well, on the calculator we go to second, trace, and select number 4, maximum. We'll ask for a left bound. Be sure you are to the left of what looks to be the max, or the X coordinate of the max, and then a right bound. Be sure you're fully to the right of that. I think I'm safe there. And then guess, I'm going to go just somewhere in between those two. I just left arrow once. I know I'm in that interval. Hit enter. It will give me not only the X coordinate of the max, to the nearest thousandth is 4.016, which I'll write down, but it also gives me the amount or concentration of medication at that point, which will answer the next question, which is 1.386. So going back over here, it says what will, or after how many hours will the concentration be highest? We have 4.016. What will be the highest concentration? It is 1.386. Part D, at what time will the medication be completely out of the bloodstream? Completely out of the bloodstream. That would mean we have a concentration equal to 0 up here. And so this is equivalent to finding the 0, or zeros, on the graphing calculator. I'm saying 0 because it looks like the other one is, well, it's not exactly, but it's pretty close to 0. You see this number 0.114, that would be one of the zeros. See here, 0, no, I can't tell. Actually, you need to plug in 0 for y and then solve for x, but it looks like pretty close to the origin. We have one of the zeros, we have another 0 over here. So we're plugging in y, 0 for y, and then solving. So calculator will do that for us. Looks like we're at 0, 0.114 is where this point is. That's the y-intercept. And so the x-intercept actually might be a little bit to the, just a little to the left of that, so slightly negative value. We'll go ahead and find this one over here where my little finger is. So right over here where that arrow is, that's the one we care about. Over here is pretty close to the origin. That's like when you first took the medicine and are taking medicine into your body, it maxes out and it's going to start to leave the body. So go to second, trace again, hit number 2, 0, and the 0 we want is over here, so that's a good left bound right there. And I'm going to get a right bound, make sure my little cursor is below the x-axis, looks to be safe right there. I'm going to hit enter for right bound, and then I'm going to left arrow just once to get me in that interval for my guess, and it's giving me this value 2e negative 13. That means 2 times 10 to the negative 13. That's essentially 0, very close to 0. That's the calculator's estimate. And the x value is 7.356. So at what time will the medication be completely out of my bloodstream or out of the bloodstream? It's at 7.356 hours after you took it. And I wasn't given a time at which I took it, so we'll leave it at that. It says, to be allowed to drive home, a patient needs to have a concentration below 0.39. If the patient is injected with medication at 7:30 a.m., at what time can he or she drive home? So here, we have a slight change in our function here. Instead of it being 0, I'm going to find out when it's equal to 0.39. So I'm going to go over here to y equals. I'm going to create another graph, a horizontal line at 0.39. Go ahead and graph it. And what I want to do is find the intersection over on this end between that blue and red line, the line y equals 0.39 and the function given to me for C of t. So I will do that by going to second, trace, and this time I'm going to choose number 5, intersect. So we'll have used all 5 of these calculate functions on the calculator, so these top 5. So we'll go to number 5, select that one, and it's going to ask for first curve, second curve. I only have 2 curves here, and then a guess. Now here I want to get my guess a little closer to the other end here, otherwise it's going to give me that one real close to the origin. So my guess, and it gives me a 6.974. So 6.974. So back over here, we have, if I change 730 to a decimal, 7.5 plus 6.974, and add the 2 together, and I get about 13, let's see, 13, 14 point 2, that's 50, it's 124, so it's 14.124. And time-wise, if you take just this part of it and multiply it by 60, so 0.124 times 60, you will get, let's try that quickly, 0.124 times 60. So we've got, put out of here, 0.124 times 60. 7.44. Where I got 0.124. Let's go back again here. 7.974. Let's see. So let's just double check that. So 7.5 plus 6.793. 14, I'm sure right at the 7. Okay, so 14.293, and I want to take the 0.293 times 17.58. So let's see here. So 13, 14. It should be actually 14.474. If you take 0.474 times 60, you get about 28 minutes. So 14 would be 2 o'clock in military time, and then add another 28 minutes to it, so about 2:28. So over here, let's fix that. Over here, we got 0.474. It was. Just double check that. 0.474. Okay. If you take 0.474 times 60, you get about 28.44, so that's in minutes. So if you'll remember from the tidal sine wave project, we were dividing their hours and minutes by 60 to get it as a decimal. Here we're multiplying by 60 to get it back into hours and minutes. So it would be at approximately 2:28 p.m. That person would be safe to drive home. That's problem number 1. Let's go ahead and move on to problem number 2, keeping those calculators handy. We're going to first write an equation on problem number 2. Clear the ink here. And then we'll go ahead and pop into our calculator, go through some of the processes. I'm not going to go as much detail, but some of the processes in terms of finding the max value as well. So it says an aluminum can has a capacity of 245 cubic centimeters. The top and bottom of the can are made of an alloy that costs 0.06 cents per centimeter. And that's not a mistake, it's very inexpensive, so it is 6/100ths of a cent per centimeter squared. It's the top and bottom. The lateral area is even less expensive at 0.04 cents per centimeter squared. So this is express the cost C of the material for the can as a function of the radius R. So we will do that first. So our equation here is C of R, cost with respect to the radius R, equals 0.06, that's the cost for the top. Now the top of the can is made up of 2 circles. And one of them is pi r squared, another one is pi r squared. Put those two together and you get 2 pi r squared. Now the lateral area, we're going to multiply by 0.04, is made up of a rectangle. And the rectangle has a circumference right here matching the circumference of the circle. That's actually the length of the rectangle matches the circumference of the circle. Circumference of a circle is 2 pi r, so we're going to label that 2 pi r, and this the height. So we have 2 pi r h. Now, we need an equation in terms of one variable, and so we'll do a little substitution here. We're going to go back up here. We see that the aluminum can has a capacity of 245 cubic centimeters. I know that the volume of a cylinder is pi r squared, to represent the area of the bottom right here, times the height. Now if I solve that for height, I get height equals volume divided by pi r squared. And if I know the volume to be 245, I've got 245 over pi r squared that I can use to replace h in this equation. So h right here is going to get substituted out for 245 over pi r squared. So let's erase this. And we're going to place in here times 245 over pi r squared. The pi's cancel out. One of the r's cancels here, leaving an r on the bottom. And if I rewrite that, I have Place this over here. Okay, so we have here cost equals, if I multiply the 0.06 times 2 pi r squared, I get 0.12 pi r squared. And it does help to simplify this a bit before you type it in your calculator. And then I have plus 19.6 divided by r. And so that's what I'm going to plug in. All right, so back to our calculators here. We're going to type that function in. Show you what it looks like as we type it in, and then we'll quickly do the max and the min. So I got to clear these out from the last problem. I'm going to type in, I won't be using r, I'm going to use x again, 0.12 at the second, and the little caret key over here for the pi button, and then x to the second, and plus 19.6 divided by x. Alright, so it says what radius would result in the least cost for the can? So now I'm asking for a minimum value. If we go ahead, we want to think about graphing this, and graph it here. This is graph with my, as you can see, just a little piece of it showing up here. So I was in standard graphing window. Looks like I need to change my window a little bit. Really just care about x from 0 up to maybe 10. 10 might be okay. You can think about a reasonable domain here. 10 seems to be about right in terms of y values. Probably going to be around 10 cents or so. I might want to make my y min 0, and my y max might want to make it go up a little bit higher here. Maybe to 20 or so, going by 2s, and we'll try graphing it again, see if we can, there it is. That's good enough. That's the only portion of the function we care about. We're going to now go to second trace. This time calculate the minimum. And it's going to ask for left bound and right bound, and guess again. Left bound and a right bound. Yes. It looks like we have an x value of about 2.962 centimeters, giving me, you'll see y is the minimum cost that we can. So if I have a radius of about just under 3 centimeters, I can keep the cost of making the can down to about just under 10 cents a can. So let's go ahead and write those down. So the radius would be 2.962, and as we saw on the calculator, it gave us a cost of about 9.925 cents. The last part of this, part D, says how much does the top of the can cost to produce? So the top of the can is just the pi r squared part of it, which we're multiplying by 0.06. And so we'll put approximately equal to. The radius that gives us the minimum cost for the can is 2.962, so we'll put 2.962 in here. Calculate that, you get about 1.654 cents. Alright, so that's number 2. We're going to move on to number 3 here. Number 3 says a new model BMW convertible is designed and produced to be released in the North American market. The BMW Corporation has a limited number of the new models available. The number N purchased in North America 2 weeks after the release is given by N equals 100,000 over 1 plus 10e to the negative 2t power. How many convertibles were produced? So that's this is how many convertibles. It's kind of like the carrying capacity that we talked about. This is actually a logistics equation, and you'll see the value up here is going to represent how many were produced. So that's the 100,000 cars. Then it says how many convertibles will have been purchased 1 week after release. So we should check and see. It says the number N purchased in North America T weeks. So T is in weeks. So I can plug in 1 for T. So this would be N equals 100,000 divided by 1 plus 10e to the negative 2 times 1 power. That can all be done in my calculator. I should probably show you one example of this. Make sure you get that equation written into the calculator correctly. So it would look like this. There are a couple options actually. We could just type it in here, or we could have gone to our y equals menu and typed it in there. It doesn't hurt to do that and use value. It says how many convertibles will have been purchased 3 weeks after release. We're asked that as well. So it doesn't hurt to just go ahead and type this whole thing into the function here. Although, I don't have to scale it. Maybe I don't want to do that. Let's not do that. Here's why. You would have to scale it in such a way that it would include that 100,000 in there. You don't want to mess with that. Let's do this. Type in 100,000. We're just going to do the calculation here. Divided by, and then in parentheses on the bottom I have 1 plus 10 second, and the e is here at ln, e to the negative 2 times 1 power. And hit enter. That's what it should look like. We get 42,493. 42,493. And all we have to do in the next one is change this 1 to a 3. So if we change that 1 to 3 and hit second, and then the enter button, it will recall that line, arrow back, and change that to a 3. Hit enter again, and we get 97,581. So 97,581 3 weeks later. And it says from week 1 to 3, what is the average number of convertibles produced per day? Well, average value, or average number, or average rate of change, if you will, let's call it that, but average per day, that's what this is. An average number of convertibles purchased per day is an average rate of change. We can get that by doing the slope formula. You take f of the 3 week one minus f of the 1 week one divided by 3 minus 1. F of the 3 week one was 97,581. F of the 1 week one was 42,493. Divide that by 3 minus 1, which is 2, and we get, whoops, actually it says per day, sorry. So 2 won't work. Or with 3 and 1, we actually are in days, not weeks. So that would be the average value per week. Days, I'm going to have to go change this. 3 weeks becomes 21 days. 1 week right here becomes 7 days. So 21 minus 7 is 14. So that value is going to be 55,088 over 14, or 3,935 cars per day. So you got to watch your units on that. It's asking for per day, not per week. So that's why this is a 21 and a 7 rather than a 3 and a 1. And all we need up here are the Y values, so we're fine on the top. It says E, when the number of vehicles purchased reaches 60,000, the price will jump up $3,000 due to demand. After how many days will the price jump? So here we're being asked to take the, it says the number N purchased in North America. Okay, so 60,000 will go in for the number N, and that's going to be equal to 100,000 divided by 1 plus 10e to the negative 2t power. And we're going to solve that actually for t. It would be helpful even just think of this as a proportion. and we could cross multiply. We can move this up here, so 1 plus 10e to the negative 2t gets moved up to the top up here, and we've got 100,000 over 60,000, which is going to reduce down for us here. So we have 100,000 divided by 60,000. Now a few more steps left to do. We would, to get e to the negative 2t by itself, I'd have to subtract 1 over, so subtract that 1 over. And then to get completely by itself, divide by 10, so I can throw the 10 over here. And then we can take ln of each side to bring that down, so negative 2t equals ln of this mess. And then that whole thing will need to be divided by negative 2. Get rid of this here, and then I'll have my time t, and it's going to be my time t in weeks, and then I'm going to have to multiply that by 7. So my time t in weeks, plug that into your calculator, should be about 1.354. So 1.354 weeks. Take that and multiply it by 7, and I get about 9.5 days. Double check that on your calculator. Be careful as you plug this all in. And the other option would be to take, probably take the function and graph it as well, and go through and find it that way too. But that's algebraically solving for t. All right. That's number 3. We're going to move on to number 4. All right, number 4, it says the blood alcohol concentration, BAC, is a measure of the amount of alcohol in a person's bloodstream. For example, a BAC of 0.04% means that a person has 4 parts alcohol per every 10,000 parts blood in the body. Research suggests that relative risk R can be modeled by the equation R equals E to the 16.82x, where x is the percent concentration of alcohol in the bloodstream. I underline percent just to show that you don't need to change it to a percent. It already is a percent. So it says, what is the relative risk if a person has not been drinking alcohol? So part A says, that's basically asking, okay, if we plug in for x is the percent concentration of alcohol in the bloodstream. If that is at 0, we have R equals e to the 16.82 times 0, or e to the 0, which equals 1 here. So what is the relative risk of a person who has not been drinking alcohol? It starts at 1, so 1 there. What is the relative risk if a person has a BAC of 0.17? So here we're going to go R equals e to the 16.82 times 0.17, and we're going to plug that into our calculator like that. Let's go ahead and clear this. We have we are typing in 16 second e to the power of, I believe it was 16.82. No, I didn't do that right here. Let's try that again. Not 16. Okay, so it was second e. 16 goes up in the power. 16.82. And then we can just use parentheses to type in 0.17 and hit enter, and we get 17.451 is the relative risk. And you compare that to a 1. So 17.45, quite a bit higher than a 1. So 17.45 is the relative risk. It says develop a function for percent concentration x as a function of relative risk r. In other words, that's asking you to solve this equation for the power for the x. So we would do that by taking r equal to e to the 16.82x, and taking the ln of each side. So it's ln of r equals ln of e to the power of 16.82x. So that gives us ln of r equals, move the 16.82 out in front, times x, and the ln of e is just equal to 1. Divide each side by 16.82, so x equals ln of r divided by 16.82. So take ln of each side. There's my function for percent concentration. X is a function of relative risk r. So now I'm ready to just solve this next problem by plugging in the r given to me. I'm given a relative risk of 100. Find what BAC corresponds to that. I just plug in 100 in place of r and divide by 16.82. Plug that in my calculator, and I get 0.274%. It says if the law requires that anyone with a relative risk of 4 or more should not be driving, so relative risk of 4 or more should not be driving, at what BAC should a driver be arrested and charged with a DUI? So what we're going to do on this one is use our same equation as before. This time we're going to plug in a 4 divided by 16.82, and I get 0.082%, I think is the where we are on the law currently. So, all right, that's number 4. Alrighty, so let's go on and we'll erase this. Go on to number 5. It says an open top box is to be constructed from a 10-inch by 16-inch piece of cardboard by cutting congruent squares from each corner and throwing away those squares. What are the dimensions of the box with maximum volume? So if you picture here we've got 16 here by 10 here. We're going to cut same inch squares out of each corner, fold up the corners, and create an open top box. So the question is, what are the dimensions of the box with maximum volume? We need a function to go with this first of all. So if you call this x, this be x, these are all the same. This dimension now from here to here is 10 minus 2x, and from here to here is 16 minus 2x. The height, of course, is x. That's how much it would be folded up. So if volume is equal to length times width times height, my volume function in this case, all in terms of x, would be equal to 16 minus 2x, 10 minus 2x times x. And I'm just going to leave it in that form. So it says, what are the dimensions of the box with maximum volume? I'm going to plug it in just like this to my calculator. Y equals, I'm going to plug in x, and then 16 minus 2x. Might be helpful as well to think about a reasonable domain here, 10 minus 2x. Think about it, I'm going to have no volume in my box if x is anything bigger than 5. If I plug in 5 into this last expression right here, I would get 0, and then I'd have no volume box. So 5 would be the biggest piece I could cut out of each side. So my reasonable domain is 0 to 5. So I want to go to my window here, and let's call x min 0, x max 10 will probably actually work. The other thing I need to think about is what kind of volumes I might be getting. If I plug in something like 3 to this function, I'd get 10 times 2 times 3 is 6. That would be 4 times 10 is 40 times 3, 120. Somewhere in the 100 something or other for cubic inches. So just considering my domain is between 0 and 5, let's just go 0 to 5, go by ones. My range, start at 0. I know it's not going to be negative volume. Remember, y is my volume. My y max, it's got to be somewhere in the hundreds. I better get it up to about 200 maybe. Might be a little better. And then scale it by 20s, perhaps. I'm going to hit graph. And you'll see that I get the whole portion of the graph that I want in my calculator screen there. So there it is. So that just typed in my function. And I'm now going to find the dimensions of the box, the x value of the box with that will give me maximum volume. So once again, I'm going to go to second, calculate, this time max, and it's going to ask for a left bound and a right bound. Do that real quickly here, left bound, right bound, and then a guess. And I get about x equals 2 with a volume of 144. So let's keep that 144 in mind. So volume of 144 and x value of 2. Let's see if we can fill all this out. So max volume was 144 cubic inches. I could see that on the calculator. If I get x equals 2 here, 2 inches, then my dimensions, if I plug 2 into this, 2 times 2 is 4, that's 6, and then into here, 4, that's 12. So I've got dimensions of 12 by 6 by 2 inches. That's what my open top box kind of would look like after I cut out those 2-inch squares. It'll be 12 inches long, 6 inches wide, and 2 inches high. So those are the dimensions of the box with maximum volume. Maximum volume is, of course, 144 cubic inches. That's what you get by multiplying those three values together. It says, what percentage of the surface area is being thrown away to create a box with maximum volume? So if you figure these little guys over here are 2 by 2, and there's 4 of them, I've got 2 times 2, which is 4, and then we said there were 4 of those, so that's equal to, we'll put equals, say that one of them, this is one cutout, is 4 inches, and so all 4 would be 16 inches. And so I have 16 inches out of the whole thing. So the percentage of surface area being thrown away is 16 inches out of 10 by 16, or 16 over 160, which is about 10%, actually exactly 10%. So 10% is being wasted. And it says D, if the volume of the box must be 120 cubic inches to hold an item, what size squares would have to be removed? Okay. A couple different ways you could do this. This is asking me to plug in into my calculator, the y equals menu, 120 to my equation. So let's go back to here. If my volume equation is volume equals 16 minus 2x, 10 minus 2x, and x, I'm being asked to plug in 120 right here for v. Now, a couple different ways to solve it. One would be to call this your y1 and this your y2 and find the intersection. Another way to do it would be to move the 120 over to the other side here and set it equal to 0. So 0 would equal 16 minus 2x, 10 minus 2x, x minus 120. Either one will work. I think I've demonstrated the intersection one on that. We had the one where it had the 0.39, and we demoed that. But if I move that over, that's probably the easiest. Well, either one, not difficult. But I can just go right over here and subtract a 120 off the end, and then use the zeros function. So we're going to go minus 120, which is my new function. I'm going to go to second, trace, calculate 0. And I calculate the 0 of this thing. Just going to graph it first. A little slightly different function. It's going to ask for left bound. Left bound and a right bound. Left bound and a right bound, and you go off the screen here. See that I have a couple different solutions here. My right bound's off the screen. Go back a little bit. Do a guess. So one of them is x equals 3. Let me change the window just a little bit. Let's give a y and a negative 20 and a y max. Not quite so high. How about 100? Graph it and see what happens. So we had x equals 3 was one of them. The other one, so you can see it goes right through x equals 3. This other one is right here. I'm going to hit second, calculate 0 again, and I'll do left bound over here. Left bound here, and a right bound over here, and then do a guess. I get 1.127. So let's write those two down. We've got 1.127 inches. Or the other one is 3 inches. All right. That's what we have so far. That's through problem number 5. I'm going to pull up. I have a different problem 6 here than what you're seeing right here, so I'm going to pull that up in a minute. Okay, problem number 6. This goes with our tidal sine wave project. So we're going to go ahead and find a trigonometric equation for this and then use it to answer some questions. So it says in a harbor, high tide occurs at 1:30 a.m. and 1:30 p.m. with a depth of 16 feet. Low tide occurs at 7:30 a.m. and 7:30 p.m. with a depth of 7 feet. Assume t equals 0 corresponds to 12 a.m. All right, I'm going to try and get a little more space here. Zoom in a bit. That's too much. I'm going to draw a picture down here, so we have a picture to go with. Get a picture of this guy. All right, so we have several things we need to find out. We need to find out the amplitude. We're going to have to find out the period and then use that to get B. We're going to have to find out the phase shift and the vertical shift. So let's start plotting some points here. It says at 1:30 a.m., so that would be about 1.5 into the cycle. 1:30 would be about 1.5. We've got a depth of 16 feet. That's the high tide. So up here is high tide at 16 feet. And then at 1:30 p.m., 12 hours later, that would be 13.5. We've got another high tide, and then we've got a couple low tides in between. So it occurs at 7:30 a.m. and 7:30 p.m. So it's 7.5 here. And then here we have somewhere around here is 13.5, and then 7:30 would be in military time. 12 plus 7.5 would be 19.5. So I've got high tides at 1.5 and 13.5, and then low tides here at 7, at 7.5, and 19.5. So I'm going to draw my sinusoidal graph. It looks something like that, and just keep on going there. So that is modeling my tides. All right, so to find the amplitude, I need to split these in half here. Going to find the midline in here. And the midline is going to be somewhere around there. It's halfway in between these two, between 16 and 7. So you go ahead and add 16 plus 7 and divide by 2. 23 over 2 gives me 11.5. So my vertical shift is 11.5. Marking this as 11.5, you can easily see the amplitude is going to be 4.5. It's 4.5 above or below. The way we kind of laid out the 4 steps, finding these 4 pieces in that tidal sine wave project, we added the high and the low, divided by 2 to get the vertical shift, and then we subtracted the high and the low, and divided by 2 to get the amplitude. So that's the amp. This is the vertical shift. Pretty easy to find. If I'm going to use a sine function to model this here, I can figure that it starts at right on my midline, maybe right here, and then goes up. We'll have to look at a possible phase shift here. We could also write a cosine curve to this. That would work as well. I think I put the sine curve in as our function that we were using to model. But either way here. So let's go ahead and we can actually find both. Maybe we'll just find both. So I'll show you the sine curve as well as the cosine curve. So it says we got to find our period. Okay, so period, we're going to look at the two high points here and here, and it's no surprise that the period is 12. If the period is 12, that means b can be equal to the value 2 pi divided by 12, which is pi over 6. So that's my b in the equation, is pi over 6. And I just have to figure out the phase shift here. So I got to figure out a phase shift for this guy. And let's see here. There we are at. You can see right here, from here to here, it really looks like a cosine curve. Maybe easier to write cosine curve first. But if I continue going at the same rate here, we're going to go actually in the same direction the other way here. If I continue going the sine curve here, looks like a sine curve. I would go from about here to here. So yeah, maybe a cosine curve would be easier first. Let's do the cosine curve, and then we'll go back and talk about how we can figure out the sine curve. So the phase shift here, pretty easy to see if I use a cosine curve. The phase shift is 1.5 over. So just 1.5 here over. So I'm ready to write my cosine function. So as a cosine function, I would have d equals, d, or depth, equals 4.5. See that it starts high, so I don't need to flip it. Cosine pi over 6 is my b. I've been shifted 1.5 units over, and then plus 11.5. In terms of a sine curve, the sine curve is just going to be pi over 2. It's kind of about pi over 2 out of phase with this. So okay, so if you want to write a sine curve for this, it's probably helpful to graph it. It doesn't hurt to graph it, but basically we're going to be 90 degrees shifted from our graph. I kept going here, 90 degrees shifted to the left, and what you're going to find is that 90 degrees shifted over here. I'm going to find that so let's go ahead and graph this thing. I think that's the best way to see it. So we have 4.5 cosine second pi divided by 6, and in parentheses I have x minus 1.5, in parentheses plus 11.5. Probably a good window here is going to be going from maybe 0 to 24-hour period. We go by 2s. Y min maybe of 0 would work. Y max of about 20. Remember, I'm ranging from like 7 to 16 on my tides. Y scale of 1. Graph it. So there's my curve. What you'll notice here, let it finish, is if you want to figure out where, if you hit trace here, kind of want to figure out where this thing frozen. Great. Okay, give me a moment here again. Okay, so if you do a trace on this thing, as you go to the left here, you can see different places where you could start that sine curve. Somewhere, you want to start somewhere when y is right on the midline, so around 11.5. You can see it's not going to hold right at 11.5, but you know, it could be shifted 10.545 to the right. You could also shift it to the left. I was going to go over here to the left and see where, as I keep tracing here, what value of x I could plug in to see where my sine curve would be about 11.5 again. Remember, the sine curve is going to start on the midline. There it is, right there. So at about negative 1.5 would be a good spot there. Negative 1.5-ish, somewhere in between those. So negative 1.5 is probably a good spot to do that, to say that, okay, that's where I'd shift my sine curve if I were to use that. So just to be consistent, you'll get pretty much the same answers if you change this to a sine curve and change that phase shift to plus 1.5 on there. You'll be about right for our curve. So let me go back here. I'll write down a sine curve. I think this is what I have written down. I need to add the cosine curve to this. It looks like the cosine curve would be a easier model to use because we're given the high tide and the low tide, and we can use the high tide as our phase shift, that first high tide directly as our phase shift. So sine curve would be 4.5 sine pi over 6 t plus 1.5 plus 11.5. Once again, I think I would go ahead and use this. I'm going to change it on the answer sheet. I think that cosine curve is easier to use just because this is the natural breakdown. If you look down here at the picture, just from high tide to high tide, we have a nice cosine curve with a period of 12. It says, what is the depth of water at noon? That's just a matter of plug in, make sure you're in radian mode, plug in 12 for t. If you plug in 12 for t, you should get 14.682 feet. And you get that with either of those functions. At what times is the depth 14 feet? So this is asking you to plug in 14 here and then solve. And I can get approximate times just by doing a trace on my calculator. We're going to get them in 12-hour minutes here. So actually, no, we're going to get two different times here where it's about 14 feet. So if I go back to my calculator, do a trace here. I'm looking for when it's about 14.5 feet. So it looks like, there's a 0. It's coming back down. I don't want it when x is 0. But, so we are, keep going, right, pretty close to that's 3.09 approximately, it looks like. And and I just keep cycling through and find all the places in a 24-hour period at which the depth is 14 feet. What I can do here is go over here, find a horizontal line at 14 and graph it. It's just a matter of finding all the intersection points. We don't care about this one, that's at 0, less than 0 time, but we need this one. So it's right here, here, and here. So a few different times there. I think I might have one more over here to look and see what I set my window to. I could change it on here. So x min of 0, x max, I want it to be 24. Hit graph, and then let's see, I think all 4 of them that I'm going to have in a 24-hour period. So there are actually 4 different times separated by 12 hours at which I have a depth of 14 feet. So 1, 2, 3, and 4. If you want to find those, you go to second, calculate, intersect, number 5, and first curve, second curve, guess. So one of them is 11, so x equals 11.6249, 11.62, about 11.625. And going through that same process, you'll get 4 different values. Let me write them down here. I'm going to erase this over here, and so we get 4 different times. They are 3.375, again at 11.625, again at 15.375, and again at 23.625. So you'll notice that these are 12 hours apart, these are 12 hours apart. So if I can convert this one over and then just add 12 hours to it. So 3.375, you got to multiply the 0.375 times 60, and you'll get about 22 minutes. And so that first point on the graph at which it hits a depth of 14 feet is at 3:22 a.m. and it's also going to be at 3:22 p.m., 12 hours later. And then the 11.625 value gives me a time in the same way of 11:37 a.m. and p.m. So 11:37 a.m. and p.m. So if you add 12 hours to it, the 23.625 is the 11:37 p.m. So there we have it. Okay, last one on here. It says a business, this will be done on the calculator as well, allows visitors to dive off their pier into the harbor. Because of safety issues, though they can only dive when the water depth is at least 12 feet. So business is open from 8 a.m. to 7 p.m. During what hours can visitors dive into the harbor? So here I can change on my graphing calculator my X-Men and Y-Men. That'll be helpful here. So I'm going to go from 8 a.m. until 7 p.m. 7 p.m. Let's actually go one less than that, so we can see 7. So 8 a.m. and then 7 p.m. would be at 1900 hours military time. So we could go maybe 7 to 20 here, going by 2s again. So graph this thing. Oh, and we need to change our horizontal line to 12 feet rather than 14 feet. So let's go ahead and do that. For y equals, change that second one here to 12 feet. Graph it. Graphing our cosine or sine curve, either one you want to use, doesn't matter. And it's going to graph our line y equals 12. So we can only dive between, when they're open, between 8 a.m. and 7 p.m., which goes from the left-hand side over right about here to over to here. And then we need to know that the depth has to be at least 12 feet, so here and here. So we've got to find the intersections at those two places. Of course, you could also subtract that 12 over and use the 0 function if you wanted to as well. But we are going to find intersections. First curve, second curve, guess here. It's going to get one of them. So one of them is 10.713. So next is 10.713. And then the other one, through the same process, will give you 16.287. So we've got 10.713 is one of them. 16.287 is the other one. And if I go ahead and multiply this portion by 60 and this portion by 60, it will give me the minutes. So we've got 10:42 a.m. Once again, if you remember, in our tidal sine wave project, we were given the time in hours and minutes of the high tides and low tides, and we divided by 60 to change it to a decimal. In this case, we're going the other direction, so we're taking 0.713 and multiplying it by 60, and that gives me approximately the 42 minutes. It'll be 42 point something, I think. Same thing with the 16.287. 16 would be 4 hours past 12, so we've got 4, and the 0.287 times 60 gives me about 17 minutes past the hour p.m. So those are the hours in which they can dive in the harbor. All right. That's it for the performance task. Final review.